Let's continue ZEUS training, Section 11, Flutter Analysis. So in ZEUS, the Flutter analysis is very similar to ZEUS in that the Flutter module in ZEUS solves the frequency domain Flutter equation using the G method and the K method. And the majority of the computational effort is to generate the frequency domain generalized aerodynamic forces, or the GAFs, from the Euler solver module. And we have three methods available in ZEUS for the generation of these GAFs. The first is the sinusoidal excitation technique. Next is the composite sinusoidal excitation technique. And then finally, the frequency domain linearized Euler solver. And we would recommend using the frequency domain linearized Euler solver. And the majority of the input cards for the Flutter analysis are identical to those of ZEUS. So the three methods in detail. First, the sinusoidal excitation technique. Step 1 in ZEUS is to perform a steady aerodynamic computation on the rigid aircraft. Next, we apply f of t equals phi I times sine of kj times t to the boundary condition of the time-accurate Euler solver, where phi I is the ith mode shape and kj is the jth reduced frequency. Therefore, the total number of unsteady computations is the number of modes times the number of reduced frequencies. Step 3 is then to subtract the steady CP solution obtained in step 1 from the time domain CP obtained in step 2. And then step 4, we apply the Fourier transform to the results of step 3 to generate the GAFs. Next is the composite sinusoidal excitation technique. So step 1, once again, is perform the steady aerodynamic computation on the rigid aircraft. And then step 2, we apply f of t equals phi I times the sum from j equals 1 to nk of e to the minus a times kj times t times sine of kj times t to the boundary condition of the time-accurate Euler solver, where of course nk is the number of reduced frequencies, a is the damping ratio, which has a default value of 0.25. So in this instance, the total number of unsteady computations is just the number of modes, because for each individual mode, we do one computation with a combination of all of the reduced frequencies present. Step 3 then is the same as the sinusoidal excitation technique, where we subtract the steady CP solution from the time domain CP solution obtained in step 2. And then step 4 is apply the Fourier transform to the results of step 3, and then divide the results of the Fourier transform of f of t to then yield the GAFs. So you can see that these are both time domain solutions, and then we convert the time domain solution to the frequency domain. The last is directly solve the GAFs in the frequency domain. So the frequency domain linearized Euler solver, step 1, we perform the steady aerodynamic computation to provide the steady background flow solution to the linearized Euler solver. And then step 2, perform the frequency domain linearized Euler computation for each reduced frequency and each mode shape to directly yield the GAF. And similarly to the sinusoidal excitation technique, the number of computations here is the number of modes times the number of reduced frequencies. So then after we obtain the GAFs, we can move on to the frequency domain Flutter solution. So the desired Flutter solution is the P method equation, which is given here. S squared times MHH plus KHH minus Q infinity times QHH of SL over V, all times C equals 0. Now introducing a non-dimensional Laplace parameter P, where P is SL over V, which is equal to gamma K plus IK, where gamma is the decay rate, then gives the P method equation as shown here. Now, because of the inclusion of gamma, the P method can provide accurate gamma in the pre-flutter condition, where gamma is less than 0, and the post-flutter condition, where gamma is greater than 0. This should be gamma greater than 0. And then accurate gamma in the pre-flutter condition can be used to correlate with the measured damping during flight flutter test. And accurate gamma in the post-flutter condition provides information regarding to the severity of the flutter. As an example here, if we have these two different damping curves, this first curve here is what we call explosive flutter, which may lead to catastrophic structural failure because we can see that gamma is rapidly increasing as V increases. And then the second one here is a hump mode where gamma is increasing slowly above 0 as V increases, and then in fact gamma starts going back towards 0 and may go negative again. So this is a hump mode which could lead to flutter, or due to nonlinear effects, it may just lead to LCO in actual flight. Now, because of the harmonic motion assumption in the ZEUS frequency domain unsteady aerodynamic methods, only QHH of IK is available. Therefore, the Flutter solution is valid only at the stability boundary where gamma equals 0. For reliable damping prediction in the complete velocity range of interest, an approximation technique for the Flutter solution is required. And 3 Flutter solution techniques are usually adopted by industry, where we have the K method, the PK method, and the G method. So first we'll review the K method. The Flutter equation is expressed in the complete frequency domain, as shown here, where the IGS, this term here, is the added artificial complex structural damping. Now, since the dynamic pressure Q is 1/2 rho V squared, and then substituting for V, the omega L over K, we get this term for Q infinity, and of course rho is the air density. Then the K method equation can be obtained by dividing the resultant equation by omega squared to give us this equation, where lambda here is 1 plus IGS over omega squared. Now for a given K, lambda can be solved by the eigenvalue analysis, and the flutter frequency omega F, the airspeed Vf, and the artificial damping Gs are then given by these equations. Continuing with the K method, now for a given set of Ks, one can generate a velocity versus damping diagram and a velocity versus frequency diagram, as shown here. Now, since the K method's numerical procedure requires only a straightforward, complex eigenvalue analysis of each reduced frequency, its solution technique is efficient and robust. However, there are several drawbacks discussed below which make the K method a less attractive method for flutter analysis. First, the solution is valid only when GS equals 0. Other non-zero damping values are artificial and may not have significant physical meaning. Next, the frequencies and velocities are computed at a given pair of Mach number and air density. This implies that the flutter boundary computed by the K method generally is not a matched point solution, where the flutter velocity Vf equals m times a. So for a matched point flutter analysis, Vf is guaranteed to be equal to m times a, but for the non-matched point analysis, this condition does not have to hold. So the matched point solution can be achieved only by performing the flutter analysis at various air densities iteratively until the condition V equals ma is satisfied. And then next, sometimes the frequency and damping values loop around themselves and yield multi-value frequency and damping as a function of velocity. We can see that with the green curve here, the tracking for mode 2. You can see that the curve is going like this, and then it loops back on itself, so we actually have multiple values for the same velocity. So this gives difficulty in tracking the eigenvalue in the reduced frequency list. And then finally, the term 1 over k indicates that the K method cannot generate a flutter solution at k equals 0. This is the reason why the K method excludes the rigid body modes from its flutter equation. And the failure at k equals 0 also implies that the K method cannot directly predict the divergent speed instability, which is an important aeroelastic instability problem. So moving on, we'll go to the PK method. The PK method equation is similar to the P method equation, except QHH of P is now replaced by QHH of IK, shown here. And now Rodden modified the PK method by adding an aerodynamic damping matrix, where QHHR and QHHI, these two terms, are the real part and imaginary part of QHH of IK. Now, for a given pair of V and rho, the PK solution is obtained by an iterative procedure that matches a given k with the imaginary part of the eigenvalue p equals g plus ik. And note that the added aerodynamic damping matrix is this term here, minus 1/2 rho v squared QHH I over k times g. This term is embedded in this term here. So continuing on with the PK method. The PK method yields a well-behaved VG and VF diagram without the loop problem as shown in these figures. And the PK method produces results directly for given values of velocity and air density pairs. This allows the PK method to provide the matched point solution if the given velocity and air density satisfy V equals m times a. And another significant advantage of the PK method over the K method is the predictability of divergent speed, where the frequency of an elastic mode becomes 0. And the VG curve of the bending mode predicted by the K method approaches the zero damping axis perpendicularly, but does not cross it, as shown here. The corresponding VG curve, or the K method, that's shown here. The corresponding VG curve of the PK method has a discontinuity in the divergence mode before divergence occurs, but it crosses the zero damping axis at the divergence speed, as shown here. And then finally, we have the G method. So the basic premise of the G method lies in the assumed existence of an analytic function of QHH of P, which equals QHH of G plus IK, in the domain of G greater than or equal to 0 and G less than 0. This premise is based on the fact that the Laplace transform of the time domain unsteady aerodynamics for divergence and constant amplitude motions is analytic. And due to analytic continuation, QHH of P is also analytic for decay motions. Thus, QHH of P can be expanded along the imaginary axis, that is along G equals 0, for small g by means of a damping perturbation method. So QHH of P is approximated by QHH of IK plus g times the partial derivative of QHH of P with respect to g at g equals 0, and this is valid when g is much less than 1. So this term, partial q, partial g, is not available from the k-domain unsteady aerodynamic methods. However, if QHH of P is analytic, then it must satisfy the Cauchy-Riemann equations. These are the Cauchy-Riemann equations, so that the partial derivative of QHH of P with respect to g equals the partial derivative of QHH of P with respect to IK. And this quantity is available to us. So now replacing QHH of P in the P method equation by QHH of IK plus g times q prime of IK, where q prime is the derivative of q of IK with respect to IK, yields the G method equation G squared times A plus G times B plus C times C equals 0, where A, B, and C terms are given here, and BHH is the generalized damping matrix. So you can see our q prime quantity here. Now the G method equation is solved by a reduced frequency sweep technique. So for a given pair of V and rho, the eigenvalue G is solved from k equals 0 to k equals k max. And the Flutter solution occurs when the imaginary part of G equals 0. And that's circled here. So these are the Flutter solutions. Now for n structural modes, the PK method and the K method normally provide only n roots of the Flutter equation, whereas the G method potentially gives an unlimited number of roots. For instance, if the exact Theodorson function is used, then the number of aerodynamic lag roots that would appear is infinite, and the extra roots are called the aerodynamic lag roots. And the importance of the aerodynamic lag roots becomes apparent when divergence occurs. The G method equation is rigorously derived using the Cauchy-Riemann equations, whereas the added aerodynamic damping matrix in the PK method has no solid theoretical foundation. And it can be shown that the PK method equation is valid only when k equals 0 or g equals 0. And QHH of ik is linearly varying with respect to k. That is, the derivative of q with respect to ik is constant. So moving on with an example here with the G method, we have a 3 degree of freedom airfoil at Mach 0, which is the MSC Nastran HA145 test case. So a non-zero frequency dynamic divergence speed is well predicted by the G method, the PK method, and the transient method, which is a time domain method. And both the G method and the transient method capture two aerodynamic lag roots which are absent in the PK method solution. And the frequency versus velocity diagrams of the G method and the transient method are in good agreement. The frequency of the free plunge mode computed by the PK method remains 0. So this results in poor correlation in the VF diagram with the G method and transient method. So our transient method is shown by the solid black line. The G method are the solid symbols and the X, and then the PK method are the open symbols. So if we look at the damping curves, you can see that the transient and G method agree well. And then when we come over to the frequency, you can see that if we look at the first elastic mode and the second elastic mode, those track pretty well. And then this mode down here, this is our lag root. So the transient method shows this, and the G method picks that up with these X's. This is a aerodynamic lag root from the G method, tracks this mode very well. Whereas the PK method, you can see originally is tracking this mode, and then it switches to start tracking this mode. And so we completely lose out on the fact that we actually have two different modes here. So the inclusion of the aerodynamic lag roots could provide important physical insight of the Flutter solutions. The results of the G method suggest that the divergence speed is caused by the coupling of a structural mode and an aerodynamic lag root and should be considered as a special case of Flutter instability. And you can see this right away from the G method, whereas this is not apparent with the PK method results. And when divergence instability occurs on a free structure, the frequency of the aerodynamic lag root could move away from 0 and be coupled with an elastic mode, resulting in divergence, as we see here. So let's move on to the bulk data cards for the Flutter Analysis, which is the Flutter module of ZEUS. So the important cards here, we have the Flutter bulk data card, which will then call out to the remaining cards. The fixed cards define the velocity and density for the analysis, and then we'll review these other cards as needed. This is the bulk data card interrelationship. So we have the Flutter card referred to by the case control section. The fixed cards define the analysis conditions. We can have modal damping defined, and let's see, we have the plot flut, which allows you to plot the Flutter mode animation. So here's the Flutter card. We have an ID number, which is referred to by the case control command. Then we have the sim field. So this is a character field. The first 4 characters must be either sim, anti, or asim. That defines the boundary condition of the structural finite element model, as well as the unsteady aerodynamics. So for a half span model, this must be either sim or anti, and for a full span model, it must be asim. And then the last 4 characters are used to specify the interpolation scheme for the generalized aerodynamic matrices. They can either be blank for a cubic spline, L for linear interpolation, or P for the second order polynomial interpolation, or an integer for the hybrid cubic spline and linear interpolation scheme. Next, we have the fix field, which refers to the fix MATM, fix Mach, or fix MDen. Next is N mode, which is the number of structural modes used in the Flutter analysis. If N mode is 0 or blank, then all of the structure modes that are imported by the assign FEM are included in the Flutter analysis. The tab DMP field refers to the tab DMP1 bulk data card, which specifies modal damping as a function of natural frequency. For 0 or blank, no modal damping is assumed. And oftentimes in our analysis, we will assume 3% modal damping. So you can do that through the tab DMP1 card. Next is the mlist, which refers to a set1 or set add card to exclude normal modes from the Flutter analysis. And if mlist is blank or 0, then no modes are excluded. For ZEUS, by excluding modes, you'll cause ZEUS to skip the computation on those modes, so you will save computational time because ZEUS won't have to compute the aerodynamics for those modes. Next, the conmlist can refer to the conmlist card, which can refer out to the conm1 or conm2 cards for mass perturbation. And then lastly, we have nk step, which is the number of reduced frequency steps for the reduced frequency sweep technique of the G method Flutter Solution. This field's only used by the Flutter discipline. Remember that the Flutter card can be referred to by other disciplines, in which case the nk step is ignored. And the default here is 25, which usually does not need to be changed. Okay, so the Flutter card is referred to by the Flutter case control command or by the mloads, eloads, gloads, or nonlinear Flutter cards. Now, if the linearized Euler solver is used to generate the frequency domain GAFs, that is done by specifying method equals 3 in the mk param card. If method is not equal to 3, then the sinusoidal excitation technique is used to convert the time domain unsteady aerodynamics to the frequency domain. The sinusoidal excitation technique is performed for each reduced frequency listed in the mk_z card and for each structural mode. And so for the given reduced frequency k, the total time t max of the time domain computation is 2 cycles of sinusoidal excitation at a given structural mode. So 2 times 2 pi times ref c over t, 2 divided by k. The 2 cycle, remember, can be modified by the param card of ZEUS. 2 is the default. So the time step is computed by t max over n step, where n step equals 201 is the default value. And once again, n step can be modified by the mk param card. Next, for the sim field, the G method reduced frequency sweep technique requires the interpolation of the generalized aerodynamic matrix from those computed at the reduced frequency list defined in the mk_z bulk data card. And the Flutter solution computed by the G method may depend on the interpolation scheme, especially if the unsteady aerodynamic computations at high reduced frequencies are not converged. Now the cubic spline, which is signified by the blank last 4 characters, provides a continuous slope of the generalized aerodynamic matrices with respect to the reduced frequency. It normally gives accurate aerodynamic damping solution because the G method shows that the aerodynamic damping is related to the slope of the generalized aerodynamics. However, if you have non-converged generalized aerodynamics at high frequencies, they may contaminate the interpolated results at low reduced frequencies. This can be removed by using the linear interpolation. However, this gives discontinuous slopes of the damping solution. So next we have the second order polynomial interpolation scheme, which selects every other 3 consecutive points and establishes a second order polynomial for interpolation, which avoids the impact of the high frequency aerodynamics on the interpolated low frequency results. However, the slopes of the interpolated results computed by the second order polynomial interpolation scheme are only piecewise continuous. So lastly, we have the hybrid cubic spline and a linear interpolation scheme, which is toggled by using an integer. So this divides the reduced frequencies into a low frequency region and a high frequency region, where the high frequency region contains the last n+1 reduced frequencies in the reduced frequency list, and the cubic spline is employed in the low frequency region, and the linear interpolation is used in the high frequency region. By doing this, the damping solution is accurate at low reduced frequencies, and the dependence of the low frequency results on the high frequency aerodynamics is avoided. For the CONM list, if it's 0, no mass perturbation is performed, but if we do refer to this card, then we can change the mass of the structural finite element model without rerunning the finite element analysis. Typical example here is fuel variation with respect to a baseline fuel weight, where the finite element model corresponds to the baseline fuel weight, which should be the full fuel, which is imported by a sin FEM. Another application of the CONM list is the fictitious mass method for accurate transient dynamic loads analysis. And then lastly, the NK step. The reduced frequency step, delta K, is defined as delta K equals Kmax divided by NK step, where Kmax is the maximum reduced frequency. And the reduced frequency step technique increases the reduced frequency incrementally by delta K to search for the Flutter solution. Normally, NK step equals 25 is sufficient to provide an accurate Flutter solution. However, if some peculiar aerodynamic lags occur, it's recommended that NK step be increased to verify the Flutter results. And you will see a warning message in the ZEUS output if it suggests that you need to do this. Next, we have the FAST card, which enables the composite sinusoidal excitation technique for the frequency domain Flutter analysis. So this card is identical to the Flutter card, except now instead of using the sinusoidal excitation technique, we use the composite sinusoidal excitation technique. So we've just gone over that a few slides ago, but here it is again. And everything else is the same. So next we have the fixed Mach card. This is the non-match point Flutter analysis using the G method. So we have a fixed Mach number with varying velocity and density pairs. And this is referred to by the Flutter card. So we have an ID field referred to by the Flutter card. Next is ID MK, which refers to an MK arrow Z bulk data card. Next we have FTM unit and FTL unit. These define the mass and length units used in the Flutter analysis, and we call these the analysis units. So the mass unit must be one of slinch, slug, pound mass, grams, kilograms, pound force, slash, or Newton slash. And I'll go over the slashes here in just a minute. The FTL unit are the units of length used in the Flutter analysis. So that must be one of inch, feet, meters, millimeters, centimeters, or kilometers. So the LBF slash and the N slash means choose the mass unit such that my given force unit is either pounds or newtons. So for example, if your length unit is feet and then your mass unit is LBF slash, that means my force unit will be pound force, and so the mass unit must be slug, since my length unit is feet. If my length unit was inch, then the mass unit would be slinch. Similarly, for the SI units, if my length unit is meter, and then N slash is my mass unit, that means my units of force will be newtons, so my mass unit would be kilograms if my length unit is meters. On the other hand, if my length unit is millimeters, which is quite common, and my force unit is newtons, then my resulting mass unit would be tons. Next is VREF, which is a reference velocity. This is used to normalize the output velocity for output. So most often you'll use VREF if you want to output the velocity in knots. So you can put the 1.68, I believe, in here. If you're doing, if your length unit is feet, you have 1.68, then your velocity output would be knots. Next we have FLUT-TF, which refers to a FLUT-TF bulk data card that defines a second order linear system. So this second order linear system is added to the Flutter equation. So you can add an arbitrary second order linear system here to be included in the Flutter equation. Next we have the print options. So the default is 0, which prints out the damping and frequency versus velocity diagrams. Additionally, we can have it equal to 2, which prints out the damping and frequency versus velocity over vref. Equal to 3 is prints out damping and frequency versus dynamic pressure, and then equal to 4 prints out the damping and frequency versus density diagrams. Additionally, print can be negative, so this prints out the generalized mass and generalized aerodynamic force matrices in the output file as well. And then lastly, we have our open-ended input, where we specify velocity and density. So this is the list of velocity and density pairs, and the units are in the analysis units, specified by FTM unit and FTL unit. Furthermore, the resulting dynamic pressures must be increasing. So in our example here, you can see that V and rho are both increasing as we move along, which means our dynamic pressure is increasing. So you start with the lowest dynamic pressure, and then you go towards the higher dynamic pressures. And we've already talked about all of that. Next is the fix MATM, which is the matched point Flutter analysis using the G method. So here, we, given an atmosphere table, we simply define the altitudes. So the new fields here, we have ID ATM, which refers to an Atmos bulk data card. You can leave this blank. So ZEUS has the 1976 standard atmosphere table built into it. So if this is blank, that's what it uses. Or if you want to define your own atmosphere, you can do that using the Atmos bulk data card. So for example, if you have a hot day or cold day that you want to define, or even if you want to do a Flutter analysis on Mars, you can define your own atmosphere table to represent that. And then our open-ended input is just the list of altitudes. Unlike the other fixed cards, the dynamic pressures start high and go low. So we start at the lowest altitude and then increase altitudes. And the altitudes are in FTL unit. And we don't need to go over any of that. Next is fix MDen, which is the non-match point Flutter analysis using both the G method and the K method. So here we have a fixed Mach number and a fixed density. So if you have a fixed density in your analysis, this card is more convenient to use than the other one where you have to specify both velocity and density. So here we have the density is in the first row, so that's a fixed density. And then our open-ended input, we just have the list of velocities. And once again, the dynamic pressures must be increasing system f of s, where f of s equals s squared times m plus s times c plus k, where s is the Laplace parameter. So we have an ID number. Next, we have the gset field flag to specify whether our mass damping and stiffness matrices are defined in the gset or the generalized coordinates, the h set. So when gset equals yes, then the matrices mass, damping, and stiff are defined in the gset degrees of freedom. And when gset equals no, the mass, damping, and stiffness matrices are defined in the generalized coordinates. So internally, if gset equals yes, ZEUS will pre and post multiply by the phi matrix to convert the gset matrices to the h-set matrices. Next, we have C1, C2, and C3, which are multipliers to the mass, damping, and stiff matrices, and the default is 1. And then lastly, we have mass, damping, and stiff, which are character strings. So these refer to the matrix names on the ZEUS runtime database. And you can import matrices onto the ZEUS runtime database by using the DMI bulk data card, the DMIG bulk data card, or the assign matrix executive control command. So the assign matrix allows you to import a matrix from the output 4 format into ZEUS. So set ID can either be positive or negative. If set ID is negative, that triggers ZEUS to do some additional computation. So this will recompute the natural frequencies of the structure. The recomputed natural frequencies are used for sorting the velocity damping frequency list of Flutter results, and then 2, compute the eigenvectors of the modified structure and redefine the generalized coordinates based on this new set of eigenvectors. Therefore, the resulting generalized mass and stiffness matrices are diagonal, and a fatal error can occur if the perturbed mass matrix is not positive definite. And then, as we said, for G set equals yes, ZEUS will convert the mass damping and stiff matrices to the H set. Mass damping and stiff can be blank, in which case they're just the zero matrices. So if you only want to perturb the mass, the easiest way to do that is define your mass matrix and then leave C and K blank. Next, we have the plot Flutter Card, which generates the ASCII text file for plotting the Flutter mode. So we have an ID number. Next, ID flut refers to the Flutter case control command, which the Flutter mode is associated with. Next, we have mode, which is the index of the Flutter mode. So the first Flutter crossing is denoted as mode 1, the second Flutter crossing is mode 2, and so on. So you must look in your ZEUS output to see the order of the Flutter crossings. So in the ZEUS Flutter module discipline output, you will see each of the Flutter crossings listed out in the output file. So the first one that appears is the first Flutter crossing, and the second one that appears is the second Flutter crossing, and so on. So if you have, say, 15 normal modes in your analysis, and then you do the Flutter analysis and you only have 3 Flutter modes, then to plot those 3 Flutter modes, those would be referred to as mode 1, mode 2, and mode 3. So those are not necessarily associated with the structure mode 1, structure mode 2, or structure mode 3. Next, we have end time, which is the number of deformed aerodynamic models within one cycle of oscillation that are generated for the animation of the Flutter mode. So remember, a Flutter mode is nonlinear, so we can't just have one mode shape. As you go through one cycle of the Flutter mode, there are no constant mode lines, so you have to have several plots throughout that cycle to view the Flutter mode. So I find that using 21 for end time gives a really good animation without making the file size too large. Next, we have the max DISP, or the maximum displacement. So the maximum displacement of any aerodynamic grid point on the model will be ref C times max DISP. Next, we have form, which is the format. So you can specify TechPlot, PadTran, IDEAS, FEMAP, ANSYS, NASTran, or NASTL. And then we have the file name, which is the name of the file, and then for the PadTran file format, we have the arrow name. So skipping down to remark 4 here, the Flutter mode is represented by the deformed aerodynamic model. Now, since the Flutter mode does not have a nodal line, it's necessary to generate many deformed aerodynamic models for animating the Flutter mode. The magnitude of the deformation of each aerodynamic model is associated with sine times omega f times ti plus phi, where omega f is the Flutter frequency, ti is the time of the ith deformed aerodynamic model, and phi is the phase angle. So ti is computed by ti is I times 2 pi over omega f, where I ranges from 0 to n time. And multiple outputs of the deformed aerodynamic model at each time step are used by the TechPlot, IDEAS, and NASTran output formats, and then animations in PadTran, FEMAP, and ANSYS are supported directly by those software. Let's see, that's all we need for that card. Okay, so let's look at a sample Flutter input deck. This is a match point Flutter analysis at Mach 0.9, altitudes ranging from minus 120,000 to positive 120,000 feet, and we're excluding the 3 rigid body modes. So our Flutter card is here. We're specifying that we only want to use the first 15 modes from our modal analysis, and then furthermore, we have the mlist field referring to the set 1 to exclude modes 1, 2, and 3. So this means that in the end, we actually only have 12 modes included in the Flutter analysis. This is a half-span model, and we're doing a symmetric Flutter analysis. The Flutter Card is referring to the fix MATM with ID 20. So our analysis units are feet and slugs. VREF here is 1.68 so that we can additionally view velocities in feet per second and in knots. And then our list of altitudes is given here. So we're ranging from a minus 120,000 to positive 120,000 feet. The MK arrow Z defines our Mach number of 0.9 and our reduced frequencies here of 0, 0.06, 0.1, 0.2, and 0.4. Meanwhile, we have the MK param card to define parameters for the Flutter analysis, and we have the method equals 3 in the MK param, which activates the frequency domain linearized Euler solver. So the aerodynamics are computed directly in the frequency domain.